Hello. Good evening. Hello. Am I audible?
Yes, sir.
Okay. Good evening. So I'm Saurabh and I welcome all of you to this live session for the NPTEL course IC engines and gas turbines. This is our second session and it is based on mostly on week 2 content. In week 2 we have learned about air standard cycles, right? Otto cycle and diesel cycles. So in this session, we will try to solve some problems, and I hope that these problems will be helpful for you to understand the concepts, and it will be helpful for you to solve the assignment problems. Okay, so we will start the session. Okay, so this is question number 1, and it is asking to identify the engine type. So basically, this was supposed to be an animation, but here it is not playing. But I will try to show you maybe in, yeah, here it is playing. So can you see that it is moving animation? Hello?
Yes.
Okay. So this is an animation of engine A, let us say. This is B. So we have to identify that which type of engines are these. So you have studied about opposed piston types. You have studied about opposed cylinder type, right? Also, you have studied about radial type of engines and lot more. So which type of engines are these? So let's start with type A. So this is radial engine or opposed piston engine or opposed cylinder type of engine. Which type of engine is engine A?
Sir, opposed cylinder.
Okay, and opposed cylinder because there are two cylinders and they are opposite, and they are along one same line, but they are in opposite directions, right? And there is one same crankshaft connecting with the pistons of both cylinders. Okay, so here you can see that this is your cylinder area, right? Right. And this is the cylinder area of another another cylinder. Okay, so two different areas, right? And two different cylinders, two different pistons, and they are in opposite direction. So this is opposed piston type. And what about this animation B? Is this a radial or opposed cylinder or opposed piston?
Sir, opposed piston.
Yes, this is opposed piston. Why? Because they are same cylinder, but two pistons, right? And they are moving in different direction. When the one piston is going towards upward direction, the second piston will be going towards the downward direction, right? So they are moving in two opposite directions, and there is same cylinder. So part B is opposed piston type, right? So part B is opposed piston type, and part A is opposed cylinder type. Okay. So in picture A, this is opposed cylinder type, but we have shown only two cylinders. Okay. But in real case, there can be more than two cylinders, like there can be four cylinders. Okay. So four cylinders means two pairs of two cylinders, right? Are you getting what I mean? So there can be more than two cylinders as well, and there will be pairs of cylinder. Okay. So in each pair, there will be two cylinders in the opposite direction. So in one piston will be going in, let us say, in upward direction. The another piston will be going in opposite direction. Okay. Here, for the simplicity, I have shown only one pair, only two pistons, but there can be more than two. There can be four or more than that. Okay, is that clear? So if it is clear, then there is one more animation. So which type of engine is this? Opposed piston or opposed cylinder or
Radial
something?
engine.
Mhm. Yes,
Radial engine.
yes, this is the radial engine, right? Again, there is same one crankshaft, and all the pistons are connected with the same crankshaft, right? In this engine, there are five cylinders, but there can be more than five cylinders as well. And these type of engines are mostly used in, you know, for your aerospace purpose. Now these engines are not that much used, but in olden days, for example, during World War era, these engines were very popular. Okay, so if you have visited any, let us say, if you have any visited where you find older engines, there you can see these type of engines. Okay, if you visit any technical museum, then these type of engines you can see. Here there are five cylinders. There is one more type of engine I have shown. So which type of engine is this?
Sir, V6.
Yes, this is V type of engine. So you know what are V type of engines? So in V type of engines, there is, your cylinders are arranged in V shape. Okay, the letter V of uh, alphabet. So these cylinders are arranged in V shape. So can you see there are two pairs of three cylinders. Okay, and these are three cylinders, and again there are three cylinders, and these are in shape V. Okay, and they are moving in a very particular fashion, in a very unique fashion. So this order in which which piston will go up, which piston will go down, so this is very intelligently designed. And the main purpose while designing these type of motion is to reduce the vibration, right? So that your center of mass should remain like that, should not move much. Okay, otherwise there will be a lot of vibrations. So these type of special arrangements are made to reduce the vibrations and for other reasons. Okay, so here engines cylinders are arranged in V shape and number of cylinders is 6. Okay, so this is V6 engine, but there can be again more than 6 cylinders. There can be like 8 cylinders, 10 cylinders, 12 cylinders, and so on. Okay, so you can get V8 engines, V10 engines, V12 engines, and so on. Okay, so these are in these type of engines are quite common, and in high end cars you can find these type of engines. Okay, so for example, here there is one engine of Mercedes Benz. Can you see? I think I should zoom it. No, no, no. Yes, now I think it will be visible. So this is V8 engine. Okay, this is V8 engine. Why V8? Because the cylinders will be arranged in shape V and the number of cylinders will be 8. Okay, so this is engine of this car, Mercedes Benz. Okay, so there can be many type of arrangements, and based on the arrangements you can categorize your engine type. Okay, so this type of category is according to how the cylinders are arranged. Okay, and another types of categorization can be like number of strokes, number of type of combustion, and so on. Okay, so again we will come to the our original file. Let us write the answer here as well so that you can access this file later. So this type of engine was opposed cylinder type. This type was opposed piston type. Okay, this was radial type of engine with 5 cylinders, and this is V6 engine, and this is V8 engine. Okay, so this categorization according to number of arrangement of cylinders, and other categories can be like 2-stroke or 4-stroke, diesel engine or compression ignition engine or auto ignition engine. Okay, so I hope this is clear, and we will move to the next question. Question number 2. Okay, let's read the question. What is the definition of mean effective pressure, MEP, in an internal combustion engine? So I think mean effective pressure has been discussed in week 2, right? So you can easily answer this. There are four options. Option A says the average pressure exerted on piston during the exhaust stroke. Part B says theoretical constant pressure that if applied during the power stroke would produce the same net work as the actual cycle. Part C, the maximum pressure achieved during the combustion process, or the pressure measured at the end of compression stroke. This is just definition. I think you can easily answer this, right?
Sir, B.
B, yes. The theoretical constant pressure, if applied during the power stroke, would produce the same net work as the actual cycle. Okay. So as you know that in 4-stroke engines, there are 4 strokes, right? One is suction stroke, intake stroke, and another one is compression stroke. And then after combustion, you have power stroke, then there is exhaust stroke, right? So pressure is continuously changing, right? So to simplify your analysis, what we do, we define a theoretical pressure which has constant value. And if that constant value pressure is applied during the power stroke, then you will get the same work output, which will be equal to the net work output of your actual cycle. Okay. So that is your mean effective pressure. So there are a lot of advantages of mean effective pressures. For example, if you want to compare two engines, right? So if you have PV diagrams of both engines, then PV diagrams can be quite different for both engines, right? But if you can calculate the mean effective pressures, then based on the mean effective pressure, you can calculate, uh, you can compare two engines. Okay. And mean effective pressure is independent of your, engine size. Okay. So this value is very important, and there will be some numericals based on this mean effective pressure. Okay. So is that clear what I mean? For example, from thermodynamics background, you know how to calculate the work output of one cycle, right? You know how to calculate that. So for diesel engine, there will be diesel cycle. For petrol engine, there will be Otto cycle. So you know how to calculate the work. Okay. But in terms of mean effective pressures, also you can define the same thing. Okay. So let us say mean effective pressure is P MEP. Okay. And displacement volume is, let us say VD. Okay. Then work output per cycle will be equal to your mean effective pressure times VT. Okay. And you know what is VD? This is displacement volume. Have you heard about this displacement volume? For example, whenever you are going to purchase one motorcycle, let us say, or bike, then you will ask how much cc engine this bike is having, right? 150 cc, 200 cc. Have you heard these terms, cc? Hello.
Yes, sir.
Okay. So what is that cc? You know what is that cc?
Sir, cubic centimeter volume.
Yes, that is cubic centimeter, and cubic centimeter is the unit of volume. So which volume is that? Is that the volume of?
Sir, swept volume.
Yes, that is the swept volume. Okay. So that is not equal to your cylinder volume. That is swept volume. Okay. So, so swept volume is equal to your cylinder volume minus clearance volume. Okay, that is your swept volume. And if your engine, if there are more than one cylinder, then you just multiply this swept volume of one cylinder by the number of cylinders. Okay. So if there are if the swept volume of one cylinder is VD and you have 4 cylinders, let us say, then it will be VD into 4. Okay. Then you will say, okay, let us say volume of one cylinder is, let us say, 300 cc, and there are 4 cylinders. Then your total swept volume will come 400 cc. Then you will call, okay, this engine is 1200 cc engine. Okay, like that you define it. Okay. And what is this swept volume, that we have already discussed in the previous session. So if anyone of you is having any doubt, then please don't hesitate. we can discuss that again. Okay, so if it is clear, then we will move to the next question. These are very basic terms. Okay, the mean vector pressure, swept volume, clearance volume. Okay, so these should be very clear. Okay, I think we can move ahead. This is question number 3, and it is saying that indicated mean effective pressure, or IMEP, is always greater than break mean effective pressure, BMEP. We have to tell that whether this statement is true or false, or we cannot say.
True.
So okay. So first of all, we should be clear about what is IMEP and what is BMEP. What is
True.
Yes, it is. Answer is true. But just for explanation, let us discuss these two terms, IMEP and BMEP. So indicated mean effective pressure is the mean effective pressure which you calculate from indicator diagram. Okay. So there is another term called indicator diagram. So what is indicator diagram? Can any one of you please tell? You know what is indicator diagram? Okay, indicator diagram is nothing, just it is PV diagram. Okay, indicator diagram is PV diagram. So indicator diagram and PV diagram both are same. So you can ask why you are giving this new fancy name indicator diagram. Just call it PV diagram. So this term comes from one equipment or one instrument that we call indicator. So in olden days, you used to have this type of instrument. Okay, this is called engine indicator. And purpose of this instrument was to give you one PV diagram. Okay, nowadays you have electronic systems, you have pressure transducers, and you have digital devices and everything you can get on your computer. But in olden days, when there was not computers, then people were using this type of uh, equipment. Okay, just briefly I will discuss how this equipment work. This bottom part, can you see this bottom part where it is where here it is written two cylinder pressure change? Okay, so this part was connected with the cylinder. Okay, so as the pressure inside the cylinder was changing, so pressure inside this indicator cylinder will also change. Okay, when you have more pressure, then it will push this piston upward. Okay, so this is not the engine piston. Okay, please don't get confused. Okay, so this part is connected to your engine. Okay, so this is engine cylinder and this is engine piston. Okay, so this is engine cylinder and this is engine piston, and this indicator is just connected with the engine. Okay, and this piston is the piston of indicator. Okay, so when the pressure inside this engine cylinder changes, pressure also changes inside this indicator cylinder. Okay, so as the pressure increases, it pushes this spring upward. Okay, so when this spring is pushed or it is moved, then this will move this rod. Okay, so this is some mechanism. Okay, and with this rod or whatever you want to call it, there will be one pen. Okay, pen or pencil that we call stylus. Okay, and there is one more mechanism here. This is your paper. Okay, this is just one paper. So here they are calling it indicator drum. So here you will be have some paper, and there is call to engine. So why this call to engine? This is for movement in this direction. Okay, in this direction. As the piston is going upward or downward, according to that, this will move. Okay, so due to the motion of this drum and the motion of this stylus, there will be some marking on this paper, right? So you will get some diagram. Okay, you will get some diagram. Okay, some diagram you will get. And since this diagram is obtained by using this equipment which you are calling as engine indicator, so this diagram was called indicator diagram. Okay, so this indicator diagram is nothing, it is just PV diagram. Okay, so this is the reason the PV diagram is also called indicator diagram. And once you have PV diagram, from PV diagram you can calculate what you can calculate. You can calculate minimum volume, maximum volume, and the profile of pressure, right? Okay, so from this diagram you can calculate the work done, right? Work done per cycle, and you have this minimum volume minus maximum volume. Okay, so let us say work done is W, and V max minus V min, this will be equal to your VD. So what you will get? You will get MEP is equal to W per cycle divided by VD. Okay, and since these value of work and volume you are getting from this particular diagram which you call indicator diagram, so this MEP is also called IMEP, indicated mean effective pressure. Okay, so this is from PV diagram. There is one more term called brake mean effective pressure. So brake mean effective pressure, this is related to your brake power. Okay, so what is brake power? Brake power is the power which you are getting at shaft. Okay, so at shaft you are not getting the same work output that you are finding from the indicator diagram, because there will be some losses, right? There will be some mechanical losses due to friction and maybe some other kind of losses. So in real case, at the shaft or at shaft you are getting less work output. But there is one term brake. Why we are calling it brake? Because to measure this torque at shaft, again we are using some another type of instruments. They are called dynamo. Okay, they are called dynamo. And one particular type of dynamo is brake dynamo. Okay, so from brake dynamo you are getting torque, and from that torque data, when you are calculating this mean effective pressure or efficiency or work output, so all those values are related to your shaft or brake. Okay, or dynamo. Okay, so just to give you idea, let us say this is your engine, this is your engine. With engine this shaft is coming, and there will be some pulley. Okay, let us say this is some pulley, and with pulley there will be some belt. Okay, or rope. Okay, right? And there will be some weights. Okay, this is pulley, and there will be one rope or something. Okay, and with rope there will be some arrangement to pull this rope down. Okay, let us say this is force F1 or F2. So when you are increasing F1 or F2, so this will be tight rope. Okay, and since this is on this pulley, so there will be friction. So more the value of F1 and F2, more will be the friction. Okay, so more friction means more torque. Okay, so this type of equipments are called dynamo. Okay, so this is brake dynamo. Okay, so whatever torque you are getting, torque will be calculated from the values of F2 and F1. So whatever values are you getting from this dynamo? From those value, when you are calculating the mean effective pressure, that is called brake mean effective pressure. Okay, or BMEP. Okay, is that clear why this brake and this indicator terms are there? Hello.
Yes, sir.
Okay, so now it is quite intuitive that you can easily tell that brake mean effective pressure will be less than the indicator mean effective pressure. Why? Because there will be some losses. Okay. So I hope this is clear. अच्छा, पिछले वाले का आंसर नहीं लिखा आपने। इसका आंसर क्या है? What is the definition of mean effect? This is part B, right? I try to write the answer so that those who could not join the live session, if they later go through this, document, they should have an idea what we have discussed. Okay. So what is the correct option for this question? True, right? It is always greater than the BMEP. Okay. So IMEP is always greater than BMEP because of losses, friction, and other type of losses. Okay. So if it is clear, then we can move to the next question. Okay, I hope this is clear and we can. Question number 4. It says that we have two engines which have identical displacement volumes and they operate at same MEP. Engine A runs at 3000 RPM while engine B runs at 6000 RPM. So we have to tell about their torque and power. So there are 4 options. Option A says that both engines will have same torque and same power. Part B says that torque of engine A is double of torque of engine B and power is same of. Part C says power of engine A is twice of engine B and torque is same. And part D says both torque and power of engine A are twice of engine B. Okay. So MEP is same. Okay. So MEP of engine A is equal to MEP of engine B. Fine. RPM of engine A, this is 3000 and RPM of engine B, it is 6000. We have to tell about power and torque. So first let's start with power. Oh, okay, let us start with torque. Let us say that torque of engine A is TA and torque of engine B is TB. Okay, this is torque. So in one cycle, in one revolution, how much angle the shaft will rotate in one revolution? How much angle the shaft will rotate?
360.
360, yes, or 2 pi. Okay, right? So the torque is T and angle is 2 pi. Then what will be the work output in one revolution? It will be torque multiplied by the angle, right? This you know, correct? Correct? Torque multiplied by the angle, you get the work output, correct? It is similar to your translation motion. In translation, what you have, work is equal to force multiplied by the distance, right? In rotational motion, this is force is replaced by
Yes.
torque, and this distance is replaced by theta, correct? Okay, so in 1 second, engine A, how many rotations it will complete? It will complete 3000 rotations. Okay, and engine B will complete 6000 rotations, revolutions. So in one revolution, work done is TA multiplied by 2 pi. So for 3000 rotations, it will be multiplied by 3000, right? In 1 second. And this will be TB multiplied by 2 pi into 6000. This is in 1 second, correct? Hello?
Yes, sir.
Hmm. So we have to compare TA and TB, right? And what is given? It is given that what is given? Same MEP. So same MEP means in one cycle, one thermodynamic cycle, in identical displacement volume. Okay, displacement volume is also same. V of A is equal to V of B. So in one thermodynamic cycle, work output of engine A will be equal to displacement volume of A multiplied by the MEP of A. And the work output of engine B will be displacement volume of engine B multiplied by the MEP of B, right? And both of these values are same. Why? Because VA is equal to VB and MEP of A is equal to MEP of B, correct? So in one thermodynamic cycle, both engines will produce the same amount of work. But since the number of rotations that engine B is making in 1 unit time, that is double of that of engine A, correct? Right?
Yes.
So engine B will complete twice thermodynamic cycles as compared to engine A, correct? So in one here, it should not be 1 second, it should be minute. So in 1 minute, engine A will complete how many cycles? 3000 divided by 2, and engine B will complete 6000 by 2, correct? These many thermodynamic cycles, because one thermodynamic cycle takes two strokes, sorry, two revolutions for four-stroke engine, right? We have discussed that in previous session, that in four-stroke engine, to complete one thermodynamic cycle, it takes two revolutions, correct?
Do you believe?
Right?
Yes, sir.
So, this is for engine A, this is for engine B, and this is number of thermodynamic cycle. Okay. So in one thermodynamic cycle, both engines are producing equal amount of work, but engine B is completing twice the number of thermodynamic cycles as compared to engine A, right? So engine B will produce twice the work output in 1 minute, correct? Right?
Yes, sir.
So 3000 by 2 multiplied by V into MEP, and this will be 6000 by 2 into V into MEP. So this is work output in 1 minute. Work output per minute. So you can clearly see that work output per minute of engine B is twice of engine A, and work output per minute or per unit time, that is power, correct? So power is double. Power of A, sorry, right? Correct? And torque. What about torque? Hello?
Force into distance. Like
Force into distance will be work output, and power is same. And in terms of torque, if you want to write power, we have already written this expression. I will write it again. In 1 minute, in 1 minute, here this side engine A, this side engine B, this will complete 3000 revolutions, this will complete 6000 revolutions. In one revolution there is 2 pi angle, so 3000 multiplied by 2 pi, this is angle, and this will be 6000 multiplied by 2 pi. And if you multiply it by the torque value, then this will be work per minute, right? 6000 into 2 pi multiplied by TB, correct? And we have seen here that 2 into power of engine A, that is 3000 into T, this thing is equal to power of B, correct?
yes.
Right? So from this expression, you can clearly see that torque of A is equal to torque of B, right? So torque for both engines is same, but the power is double, right? So both engines have same torque and power. This is wrong. Torque of engine A is twice of engine B, power is same. This is also wrong because power is double, right? So power of engine is twice of engine B and torque is same. So part C should be the correct option, right? I hope this is clear, right? So if there is no doubt, then we can move to the question number 5.
No doubt, sir.
Okay. Question number 5. Again, this is a numerical. An engine working on an Otto cycle is supplied with air at 0.1 megapascal, 35 degrees Celsius. Compression ratio is 8. Heat supplied is 2100 kilojoule per kg. And we have to find the maximum pressure and temperature of the cycle, cycle efficiency, and the mean effective pressure. Okay. So this is Otto cycle. So to start with, first of all, we should make the PV diagram for Otto cycle. So from, first of all, there will be isentropic compression, right? Then constant volume heat addition. Then in power stroke, there will be isentropic expansion, and there will be constant volume heat rejection or exhaust. Okay, so 1, 2, 2, 3, 4. So this is the Otto cycle. Okay. Air is supplied at 0.1 MPa and 35 degrees Celsius. So this, so these are the conditions at point 1, right? So P1 is P1 is how much? 0.1 megapascal, and temperature is 35 degrees Celsius. And whenever you want to solve any thermodynamic question, you should convert your pressure, temperature values into Kelvin. Okay. First step should be this, because if you miss this step and if you proceed with the Celsius values, then most probably will land up with the wrong. You will get the wrong answer. Okay.
308 Kelvin.
308 Kelvin. The compression ratio is 8. So volume at point A is, let us say it is V1 and here it is V2. So compression ratio, how do we define compression ratio? Maximum volume divided by the minimum volume. So V1 by V2 is equal to 8, right? Heat supplies is 2100 kilojoule per kg. Okay, that we will use some maybe in some later steps. We have to find the maximum and minimum pressure cycle efficiency. For cycle efficiency, it is very easy. You can just substitute in the formula, right? Or you can do all the calculations, right? How much work output is there, how much energy you are putting in, then you can divide and you can get the efficiency. But using the formula itself, you can get it straightforward, right? So what is the efficiency for Otto cycle? It is 1 minus
1 minus 1 upon r power gamma minus 1.
gamma minus 1, or let us use term k. Okay, गामा ही कर लेते हैं फिर. Rk is compression ratio, so we can just substitute the values. 1 minus 1 by 8 to the power gamma कितना है? So gamma is Cp by Cv. So
So 1.4.
1.0. Okay, so 1.4. So 1.4 minus 1, and you can calculate this value. Calculator कहाँ है? 1 minus 1
0.5647.
0.5647 let us say. Okay, so it is 56.5%. So this is cycle efficiency. What else we have to find? The mean effective pressure. Okay, that we can calculate. Sorry. Now T1 to T2, which type of process is this? 1 to 2. This is isentropic compression, correct? And for
Yes.
isentropic compression, you have this relation: P1 V1 to the power gamma is equal to P2 V to the power gamma. This is in terms of pressure and volume. But in temperature terms also you can write. What you can write? Instead of pressure, what you can use? PV is equal to nRT. From this relation you can write it. So it will be T1 times V1 to the power gamma minus 1 is equal to T2 V to the power gamma minus 1, correct? So T2 by T1, you can write it as V1 by V2 the power gamma minus 1, correct? सही है? So T2 will be T1 times V1 by V to the power gamma minus 1, and T1 is given, just a second. Okay, T2 is given how much? 308. So 308 multiplied by V1 by V2. What is V1 by V2? This is compression ratio, right? This is compression ratio and it is given to be 8. So 8 to the power gamma minus 1. So 1.4 minus 1. So 308 times 8 to the power 0.4.
700 and something.
Okay, we can use the calculator, don't worry. 308.
707.59.
How much?
707.59.
7.59. Okay, let's cross check it. Okay. Yes, it's correct. So this is what? Kelvin. So this is your T2. Now you have T2. And what we have? We also have this 2100 kilojoule per kg. Okay, heat supplied. So heat supplied, when the heat is supplied from 2 to 3, right? Heat is supplied during 2 to 3, correct? This is heat addition process, constant volume heat addition process, right? So heat added will be equal to it at constant volume pressure, so CV times T3 minus T2, correct? Right?
Yes,
Is that clear? So heat addition is given to 2100, and CV, how much? CV is 0.718, 0.718. T3 we don't know, and T2 we have just calculated 707.59 Kelvin. So this is in kilojoule per kg. Okay, fine. Or 718. This is also kilojoule in units are fine, I think. So T3 you can calculate like this: 0.718 plus 707.59. Correct, Kelvin? 2100, sorry, 2100 divided by 0.718 plus 707.
3632.38 Kelvin.
Yes, right. कितना है? 3632.38.
3632.38.
Okay. So this is T3. Now if I ask you that at which point the temperature will be highest? 1 to 2 it is compression. Okay, fine. Temperature will increase.
T3.
Sir,
And
at
from,
3.
yes, at point 3 there will be maximum pressure, because this is the end of heat addition process. So at point 3 you will get the maximum temperature, and we are asked to find the maximum temperature. So maximum temperature we have calculated. So this is the maximum temperature. और क्या है? Maximum pressure is again at point 3, correct?
Yes,
Maximum
sir.
pressure is at point 3. So we have to calculate P3. And how do we calculate T3? 2 to 3, which type of process is this? This is constant volume process, isobaric process, right?
Yes, sir.
At point 2, We can also use the ideal gas equation, right? Can we use the ideal gas equation? Hello?
PV equal to MRT.
Yes, PV is equal to MRT we can use, right? M is anyway not changing, correct? Please don't get confused. This is Otto cycle and this is an ideal cycle, and we are assuming that mass is constant and mass composition is also constant. But in real cycles, there is intake and exhaust. Okay, so this is not the actual case, this is ideal case, and here the mass is constant and composition is also constant. Cp is constant, Cv is constant, gamma is constant, R is constant. So all these things are constant. Okay, so you can use this equation for point 2 and point 3. So for point 2 it will be P2 V2 is equal to MR T2, and for point 3 it will be P3 V3 is equal to MR T3. Correct? So what you have? You have MR is equal to P2 V2 divided by T2 is equal to P3 V3 divided by T3. Right? Correct?
Yes.
So we have to find P3. So P3 will be equal to P2 V2 divided by V3 and T3 divided by T2. Correct? Right?
Yes.
And what is V2 divided by V3?
Compression ratio.
No, it is 1. Compression ratio तो ये है V2 from point 1 to 2. Point 2 to 3 it is constant volume process, right? So V3 is equal to V2, right?
Yes.
V3 is equal to V2. So you could have used the simply this thing. Sorry, here itself you could have cancelled out these volume values. Okay, but just for generalization, I have kept these values. Okay, so V2 is equal to V3. This is constant volume heat addition. This is Otto cycle, right? So P2 you already have, I think. Do we have P2? P2 दिया है क्या?
No, sir.
Okay.
P1.
Probably we need to
P1 is
calculate.
given.
Okay. P1 is given from adiabatic equation. We can calculate P2, right? P1 V1 to the power gamma is equal to P2 V to the power gamma. So let us quickly find P2. So P2 will be equal to P1 V1 to the power gamma divided by V2 to the power gamma. Correct? So P1 into V1 by V to the power gamma, and P1 is given how much? 0.1 megapascal. So 0.1 megapascal times V1 by V2 is compression ratio, that is 8, and gamma is 1.4. Okay. 0.1 times 8 to the power 1.4 megapascal. So it is coming out to be 1.837 megapascal. Correct? Say
7 megapascal.
yes, correct. So P3, let us quickly substitute this value here. P2 into T3 divided by T2. So 1.837 megapascal T3 we have calculated, I think. Yes, this is 3632.38. 363. ये सही निकाला है? Can you please check this temperature value? It is correct temperature value. I think it was correct. You already cross-checked it, right? So we will use this value and let us see. 3632.38 divided by T2. T2 कितना था? 707.59. 707.59 megapascal. And we can calculate this value. 1.837 multiplied by 3632.38 divided by 70 sorry 70 हाँ
का पास
कितना
97381 मेगापास्कल
738 मेगा पास्कल तो नहीं होगा, कुछ और यूनिट होगी।
सर 9.43 मेगापास्कल।
9.43
यस
9.43 megapascal. This is P3 and maximum pressure is at 0.3. So this is maximum pressure. So what we were supposed to find? We were asked to find maximum pressure, that is P3, we calculated. Temperature, maximum temperature, that is T3, that also we calculate. Cycle efficiency we calculated. Now we have to find mean effective pressure, right? Mean effective pressure. So you know what is the mean effective pressure? We have discussed the definition of mean effective pressure. Mean effective pressure is the work output of the cycle, right? Work output of the cycle divided by the displacement volume, correct? And work output of the cycle, this is related to your efficiency and heat input, right? And efficiency is defined as work output of the cycle divided by heat input, right? And heat input, it was given in the question, and neta or efficiency you have already calculated, right? And efficiency was found to be something 56. Okay, so work output of the cycle will be equal to heat input times efficiency. Heat input was given to be 2100 kilojoule per Kelvin and efficiency was, कहाँ है efficiency? Efficiency was 56.5. 56.5. So work output will be 2100 multiplied by 56.5 divided by 100.
118.65
Okay, 1186.5 kilojoule per kg. Okay, so this is our work output of the cycle. And what we need? Now we need displacement volume. Now we need displacement volume. Displacement volume will be V2 minus, sorry, V1 minus V2 or 8 V2 minus V2 or 7 V2, right? अब V2 calculate करना है. So at point 2 we can calculate V2, right? Hello?
Yes, sir.
Or we can calculate V1 because at V1 all these values are given. Pressure is given, temperature is given. So we will calculate V1.
Yes,
At
sir.
point 1 temperature was given to be कितना था? Temperature was 308 Kelvin. Pressure was 0.1 megapascal, I think, right?
yes sir
Right. So you can use ideal gas equation, right? V1 is equal to RT, correct? This is not capital V1, this is So V1, it will come out to be R T1 divided by P1. Okay. So R कितना दिया है? 287, 0.287. 0.287 into 308 divided by P1 is 0.1 megapascal. And to convert that thing into Pascal, R is also in kilojoule. To convert that in SI unit, you need to multiply it by this thing by 10 to the power 3, and P1 is 0.1 megapascal multiplied by 10 to the power 6. So this will be in pascals. So now everything is in SI units, right? So units are correct. Let's quickly calculate this value. 0.287 times 308 times 100.
0.88.
Huh?
0.88.
0.88.
Yes, sir.
0.88 क्या है यूनिट इसकी? मीटर क्यूब पर केजी.
Yes, sir.
kg.
मीटर क्यूब पर केजी.
Yes, sir.
And V2 will be how much? V1 by 8, right? 0.88 by 8 meter cube per kg. So this will be 0.11 meter cube per kg. Find क्या करना था? Displacement volume we had to calculate, right? So Vd or displacement volume will be V1 minus V2, right? So 0.88 minus 0.11 meter cube per
0.77.
kg, 0.77 meter cube per kg. And mean effective pressure is given by work output of one cycle divided by displacement volume. And work output of one cycle we have already calculated, right? This is 1186.5. 1186.5 divided by 0.77 meter cube per kg, and this was kilojoule per kg, right?
1540.9.
How much?
1540.9.
154.0.
0.9.
This will be in kilo
kg.
kilopascal.
Kilopascal.
Yes, because this is in kilojoule, right? So this will be in kilopascal. So please cross check this value. I hope you did the correct calculation.
Yes, sir.
Okay, so we have got all the values. We have also got the mean effective pressure. Okay, so is that clear?
Yes, sir.
Okay, if it's clear, then we will move to the next question. Question number 6. Question number 6 says, in an air standard diesel cycle, okay, this is diesel cycle, air standard diesel cycle. So air standard diesel cycle means that your working fluid is air, and air is assumed to be an ideal gas, and composition is constant, of course, because that is, air. But in real case, it is not constant. First of all, the during intake stroke, mass is not constant, right? Because more and more air is coming in. Then after compression, you add some fuel. Now composition is also being changed because you are adding some fuel. Then during combustion, composition is again changing because there will be production of uh, burnt gases. Okay, and after exhaust, mass will again not be constant. Okay, so in real case it is totally different from the ideal case, but for comparison purpose you use air standard cycles. Okay, so air standard cycle for diesel engines is diesel cycle. Okay, so this is an diesel cycle and compression ratio is 16. Compression ratio is 16. So can you please tell in the previous question which type of engine was supposed to be in previous question? Okay, the compression ratio was 8. So which type of engines it should be based on the compression ratio? Can you please tell?
SI.
It should be SI, right? So in SI engines,
SI.
compression, yes, in compression ratios are usually small. Here compression ratio is 16. So that is, it is a typical value for diesel engines, 16, 17 in that range, right? So compression ratio is 16, and at the beginning of isentropic compression, the temperature is 15 degrees Celsius. And the pressure is again 0.1 megapascal. Heat is added until the temperature at the end of constant pressure process is 1480 degrees Celsius. And we have to find the cutoff ratio, the heat supplied per kg of air, cycle efficiency, and mean effective pressure. Okay, so again we will make the diagram. Okay, for diesel cycle, first of all you have isentropic compression. Okay, then you have, yeah, then you have constant pressure, heat addition, then you have isentropic expansion or power stroke, then you have exhaust. 1, 2, 3, 4. This is your diesel cycle, right? PV diagram for diesel cycle. Now what is given? Compression ratio is 16. So what is compression ratio? Compression ratio is this: maximum volume divided by minimum volume, right? So V1 by V2 is 16. What else? The beginning of isentropic and temperature 15 degrees Celsius. So T1, so point 1 is the beginning of compression, right? So temperature at point 1, it is given to be 15 degrees Celsius, and to convert this thing into Kelvin, just add 253 and you get how much? Correct? Hello?
Yes, sir.
Yes, sir.
Okay. Pressure was given to be 0.1 megapascal, right?
Yes.
And what क्या दिया है?
T2, sir.
At the end of constant pressure process. No, it is not T2, it is T3. Constant pressure is from T2
Yes, sir.
to 3,
Okay, sir.
right? So it is T3. So T3 is 1480. 1480 degrees Celsius, and in Kelvin it will be 273 plus 1480. So 3, no,
1753.
1753
753.
Kelvin.
Kelvin.
Okay,
Yes, sir.
so let us start with the first process, that is T1 to T2. So T1 to T2, again it is adiabatic or isentropic process, so you can use the that relation. So
Sir,
T2 by
please also draw the TS diagram.
TS diagram. Okay,
Yes, sir. It is a helpful for
okay, we can,
determine temperature.
okay, we can draw the TS diagram as well. So TS. So from 1 to 2, it is isentropic process, right? So
Yes.
entropy will be constant. So 1 to 2 isentropic, so it be a vertical line. So this is isentropic process. Then 2 to 3, it is constant pressure line. So constant pressure lines, it is like these are isobars in TS diagram, right?
Yes.
Yes,
Hmm.
sir.
So 2 to 3, it is isobaric process. So along this line it will be 0.3. Then 3 to 4, again this is uh, isentropic. So it will be a vertical line, right? Constant
Yes.
entropy. So okay. And 4 to 1, this is constant volume. Okay. So
Yes. Sir.
this is not the constant volume line.
Heat rejection.
It will be
Heat is-
something like, yes. So this is constant volume line. This is volume is equal to constant. This is pressure is equal to constant, and vertical lines, they are isentropic lines. Okay.
Yes.
So 1 to 2, it is adiabatic. So we will use that relation.
Gamma minus 1.
And V1 by V2, that is
16.
16 to the power gamma minus 1. So 1.4 minus 1, right? Gamma is given, not given. So we'll use the same values that we have used in the previous question. So the 16 to the power,
3.031.
okay, 3.03.
0.03. 1.
Okay, so T2 will be equal to 288 multiplied by this value, right? 288 multiplied by
23
3.03.
873.05.
3.03.
Kelvin.
872.64 Kelvin. Okay, so this is T2. Now 0.223. This was 1 to 2. अभी चलते हैं 2 to 3. So 2 to 3, it is,
Same.
this is constant pressure, right?
Yes.
This
Sir.
is constant pressure. So P2 is equal to P3. And V3 by V2, this is called cutoff ratio, right?
Yes. Sir.
This is called cutoff ratio. And we have to find the cutoff ratio, right? You have to find the cutoff ratio. So we can use the ideal gas equation.
PV equal to MRT.
T2 V2 divided by T2 is equal to P3 V3 divided by T3, right?
Yes. Sir.
And this is constant pressure process. So P2 will cancel out P3, right?
Then B.
So
Yes.
V3 by V2 will be equal to T3 by T2, correct?
Yes.
T3 by T2. And T3 we have calculated, right? Not calculated, was given the question. So T3 was given to be 1753. T2 we have calculated, it is 872.
2, sir.
8, huh?
2. Cutoff ratio 2.
It is 2. Okay. So this is cutoff ratio 2. Okay. So now let us move from 3 to 4. So 3 to 4 is again isentropic expansion. Isentropic
Expansion.
expansion. So we will use P3 V3 to the power gamma is equal to P4 V4 to the power gamma,
Yes. Sir.
right? And
Yes. Sir.
what we have to find? We have to find cutoff ratio that we have already found out. We have to find the heat supplied per kilogram of air. So where heat is supplied, here heat is supplied in which step? 2 to 3 constant
Yes.
pressure heat addition. Okay,
Yes.
so heat addition, this is at constant pressure. So this will be equal to Q in will be equal to constant pressure के लिए Cp multiplied by
T3 minus T2.
T3 minus T2.
T2.
Okay, and Cp
is
कितना था पिछले क्वेश्चन में?
Cp for the air 1.005.
1.005. 1.005 and T3 is 1753 minus T2 is 872.64.
2-3 process is heat addition.
Huh? Sorry?
2-3 process is heat addition process.
Yes, 2 to 3 is heat addition process. 2 to 3. Constant pressure heat addition. Okay.
Eight 884.76. 884.76.
884.76.
76.
This will be in kilojoule per kg. Okay. So we got the heat addition. What else we have to find? We have to find the cycle efficiency, right?
Yes, sir.
So for cycle efficiency, what we need? For cycle efficiency, either you can use the direct formula.
Sir, compression ratio and cutoff ratio.
Yes, from compression ratio and cutoff ratio. And another way can be like the definition. So cycle efficiency is defined as the work
Sir, by
output.
net work and heat supplied.
Yes. Okay, let us do both process and let us check if you are getting the same value. So first we will do by the formula. So what is the formula? Diesel cycle. This is 1 minus 1 divided by R to the power gamma minus 1
Into beta.
Beta means cutoff ratio.
Yes.
Okay. To the power gamma minus, sorry, to the power gamma minus 1 divided by RC minus 1. Right? Sorry. So RC is your
Cutoff
RC
ratio.
is compression. No, RC is compression ratio.
Yes, understand.
No, this is compression ratio and this is cutoff ratio. Please check.
Sir, cutoff ratio can you denote by alpha?
Yes, sir.
Okay, let us rewrite the whole thing. Okay.
Sir, alpha की power gamma minus 1, that will be.
Okay, let us write it again. So diesel cycle efficiency is 1 minus 1 divided by
RC.
RC, what is RC?
Sir, compression ratio.
Okay, RC
Power
to the
gamma
power
minus 1.
gamma minus 1
Then
multiplied by
alpha power gamma minus 1.
alpha to the power gamma minus 1
Gamma
divided
into
by
alpha minus 1.
gamma into alpha minus
Alpha minus
1.
1.
Okay, so alpha is cutoff ratio, right?
Yes, sir.
And RC is compression ratio.
Compression ratio.
Okay. So we have both the values. We just need to substitute these values.
Yes, sir.
Cutoff ratio we have already calculated.
2.
Sir, 2.
Okay, इसको भी अल्फा लिख देते हैं.
Yes, sir.
Okay. Alpha is equal to 2. Alpha is 2 and cutoff ratio 16. So efficiency will be 1 minus 1 divided by 16 to the power 0.4 multiplied by 2 to the power 1.4 minus 1 divided by 1.4 and 2 minus 1. Okay. And
0.1127.
0.1127.
1127.
So if anyone else also calculated this value, then please confirm. Hello? Lot of
Sir,
noise.
please you detect this answer.
Okay. I need to mute someone. I don't know from where this noise. Okay. This is very, I mean, less value. This should not be correct. This is very less. We should get more efficiency. Please recheck.
Okay, sir. Zero point 613.
That can be,
0.61.
yes, that is a reasonable value. 0.613.
13.
Okay. So that seems a better value. In real type of engines, getting a 61% efficiency is like impossible. Okay. So most efficient engines that we have today, that will be around 40% or maybe at max 50%. But again, this is ideal case. Okay.
Only sir
Yes.
50%.
Yes, engine efficiencies are very less. Again, this is for, for cycle calculations. You are not considering the, frictional losses and other type of losses, right?
Okay, sir.
Engine efficiency will be like 40% or like that. Okay. But this is ideal case. So for 60% efficiency is fine. So efficiency we have got. What else we have to find? MEP, mean effective pressure. And one more way to calculate efficiency is to find work output divided by heat input, that you can do, right?
Yes.
Yes.
Yes, sir.
Can we quickly check, or I will leave it for you. You can check it. We should get the same value, right? Heat input is already given. Heat rejection you can calculate, and then it will be Q in minus Q out divided by Q in. So it will be 1 minus Q out divided by Q
Q.
in, and 1 minus Q out. Where is Q out? Q out is 4 to 1, right? 4 to 1. It is constant volume heat rejection. So it will be CV T4 minus T1 divided by Q in. It is already given, I think. Given, it is given or not? Q heat addition. Yes, we have calculated 8 at 4, right? So 8, 8, 4.76. T4 we already have, right? T4 we have or not? T4 you can find from process 3 to 4. 3 to 4 is isentropic process, right? So from there you can find T4. So T3 by T4 will be equal to what? It will be V4 by V3 to the power gamma minus 1, right?
Yes, sir.
So like that you can calculate T4, and you substitute in this expression, and you should get the same answer. If not exactly same, then at least of maybe 1 or 2 less or more. Okay, so efficiency. Then we have mean effective pressure. mean effective pressure, it is defined as displacement volume, right? Work output per cycle divided by displacement volume. And work output per cycle, what is work output per cycle? Work output per cycle can be calculated again using the efficiency, right? Efficiency
Sir,
into
efficiency and heat supplied.
yes. So efficiency, how much we have got? 0.613. 0.613 multiplied by heat addition, it is 884, right? 884.76 divided by displacement volume. Now we need to find the displacement volume. For displacement volume, we will have to use the ideal gas equation, right? Vd will be equal to V1 minus V2, and at point 1 you can use the ideal gas equation, right? So V1 will be equal to R 0, R is 0.287 and temperature was 15 degree, 288 Kelvin, 288 Kelvin divided by P1. P1 was 0.1 megapascal, right? So it will be 0.1 megapascal, 10 to the power 6, and here you need to 10 to the power 3, correct? Now if you calculate this value, two eight seven, hello,
Yes,
two
sir.
eight seven 287 into 288, so it is coming out to be 82 to the power minus 2, or
Yes, sir.
just 0.82, 0.8 meter
0.65.
cube kg, 0.28. I think this precision is fine. Okay, so now you have displacement volume, so now you can find MEP. So MEP will be 0.613, this is efficiency, multiplied by 884.76 divided by 0.82, so this will be in kilopascal perhaps. And if you find this value, then you get 0.613 multiplied by 884.76 divided by 0.82. So it is coming out to be 6 9 no 6 6 1, right? Correct. I think we made some mistake.
सर कैलकुलेटर में टाइपिंग मिस्टेक
4.76 divided by 0.8.
61.41.
अब सही है?
Yes, sir.
तब भी वही आंसर है 661.41. Okay. So this kilopascal, this should be the mean effective pressure,
Yes, sir.
right?
Yes, sir.
Okay, so we have got cutoff ratio, we have got heat supplied per kilogram of air, we have got cycle efficiency, and also we have calculated the mean effective pressure. So this is how we can proceed. There one more question. Which of the following statements about valve timing in an internal combustion engine is correct? So you know what is valve timing, right? You know what is valve timing? Valve timing is basically at what times intake valve and exhaust valves they are opening and closing. So that timing is
C, sir.
basically valve timing, right?
C.
Okay, let us read the options. The intake valve opens exactly at the start of intake stroke and closes exactly at the end of it.
Sir,
So this is not
C.
okay, but let us read the options first. Okay, the exhaust valve opens exactly at the start of exhaust stroke and closes exactly at the end of it. That is also not the correct. Intake valve opens slightly before the piston reaches the TDC and closes slightly after the BDC to improve the volumetric efficiency. This is correct. Valve timing
Yes,
has
sir.
no impact of engine performance. This is also incorrect. Valve timing has a significant impact on engine performance. So yes, this is correct, right? And intake valve slightly opens slightly before the piston reaches TDC and closes slightly after the BDC to improve the volumetric efficiency. So there is certain time when both intake valve and exhaust valve are open, right? So what do you call that?
Sir, overlap period.
Yes, that is called overlap. Okay,
Yes, sir.
so I hope this is clear. Okay, so yes, this was last question. So if you have any doubt whatever we have discussed, then you can unmute yourself and please raise. So if you have any other doubt related to content of week 2 especially, then we can discuss or we will stop.
No doubt, sir.
Okay. So what we have discussed today, we have discussed the types of engines. We have discussed indicator, why we call indicator. Yes, nowadays we don't use this indicator anymore because we have pressure transducer. They are very accurate and they can be controlled by computer. You can acquire the data at very higher speed. So but still this name has stuck with the PV diagram, the indicator diagram. Then mean effective pressures, how to calculate, then we solved some problems. And I hope that this session will be helpful for you to solve your assignment problems. Okay, so we will stop here. Okay, we will meet in next session. Thank you.
Thank you, sir.